Hello! This is the first of a three-part series on significant digits and how to use them in scientific measurements. And before we start, I just wanted to explain what a significant digit is. Well, basically, all measurements made by scientists have a limited what's called precision. Namely, a degree to which the measurement can be made accurately, and it's usually a consequence of what the tool is that the scientists use. For instance, here's an old analog meter stick, and each one of these markings that are numbered represents a centimeter, a 1/100th of a meter. And since each one has 9 little lines in between two numbers, we clearly also have marked the millimeters. Now, if I'm going to measure an object, say this line right here, using this device, and I line it up, well, I write down and record all places of which I am certain. Now, this line I am certain is in between 8 and 9 centimeters long, so I would record the 8 for how many centimeters long it is. And then I would see that basically it aligns fairly closely with this 0.5 of a centimeter, namely a millimeter. So I'd record the 8 and the 5. Now, all measurements in science should also include one place of uncertainty. And that is a last place in the measurement that is a best guess. And it looks to me that if this line is directly aligned with the 0.5, then I'm going to go ahead and say 0 is the next place. Now, someone else might have read it as a 1 or a 2, or they might have said this was 8.49 or 8.48. But the point being that, yeah, we should have a place of uncertainty, a best guess. Now, all of the measured places, that would be the 8 and the 5, and one place of uncertainty, the 0, would all be considered what we call significant digits. So there are 5 rules that determine which digits are significant and which ones are not. And the first and easiest rule is that all non-zero digits, that's 1, 2, 3, 4, 5, 6, 7, 8, and 9, are always significant. A scientist would not record a non-zero digit in making a measurement unless it represented a place that had actually been measured or estimated. So in the example that I give right here, clearly the 2 in the 10,000ths place, the 3 in the thousandths place, and the 1 in the ones place must be significant digits. So this number, so far as I can tell, has at least 3 significant digits. The second rule is pretty simple as well, in that any zeros that are placed between non-zeros must be significant. For instance, these 2 zeros right here in our value, they have to be significant because nobody would have measured the thousands place and then measured the ones unless they also measured the hundreds and the tens in between. So zeros between non-zeros are always significant. The third rule governs any zeros that are to the right of the last non-zero and that are in the decimal places. So if this is 23,001 and we have a decimal and there are 2 more zeros added, since these are to the right of the last non-zero, 1, and in the decimal place, that's key, then they are considered significant. And here's the reason why. I could have just as easily written 23,001 as 23,001. But if I wanted to show that I measured beyond the ones, namely whatever device I was using measured the nearest tenths, and then I would have to estimate the nearest hundredths, Well, that would make these zeros significant because they have a purpose in the value that I've written down. And so I didn't need to write them to represent 23,001, but the fact that they're there tells me something about the precision with which the measurement was actually made. And therefore, yes, they're very significant. And now for the digits that are not significant, and they also involve zeros. As a matter of fact, except for the first rule, all of our rules do involve zeros. Now this is for zeros to the right of the last non-zero, so in this number the 6 would be the last non-zero, and they are not beyond the decimal place. The decimal would be right here for 7,560,000. Now these zeros are not considered significant because they are what we call decimal place holders. They tell us that the decimal belongs right here in this value so that we read it correctly as 7,560,000. Were these zeros not here, I would read the number as 756. So their only purpose is to hold the decimal. So your question may then be, well, what about if they're to the right of the last non-zero and there is a zero in the decimal? Well, we've already learned that zeros beyond the decimal do have a key point in expressing the precision of the measurement. So this last zero now in this number is significant, and of course that puts the other 4 zeros in between significant digits. So they must also be significant, and consequently this number would have all 8 digits as significant, 8 significant figures. The fifth and final rule governs zeros that are to the left of the first non-zero, and of course we'd be using these zeros to represent small values. And these zeros serve the same purpose as the zeros we saw at the end and to the right of the last non-zero in the preceding rule. These simply are place-holding zeros. They tell us where the decimal belongs and that we began measuring with not the tenths or hundreds or thousands, but we began measuring 10,000ths, then measured the hundred thousandths and estimated the millionths. And so these are placeholders, as we like to call them, for the decimal place, and these zeros preceding the first non-zero are never significant. Now, as an added side note, what if we did have this number, 7,560,000, and we wanted to show that the precision of our measurement included the thousands and that we estimated the hundredths? In other words, if these 4 zeros are not significant, how do we make 2 of them significant and therefore a part of our measurement? And that's when we use scientific notation, because a correctly written coefficient in scientific notation, that's the number that comes before the power of 10, a correctly written coefficient must be greater than or equal to 1 and less than 10. And therefore, literally, the decimal will always be preceded by a non-zero if this has to be greater than or equal to 1. And all the zeros that are included in the coefficient would come beyond the decimal. And we've already learned that zeros to the right of the last non-zero in the decimal are significant. So scientific notation is a way to clearly show which zeros are significant and which are not, as all digits in scientific notation coefficients are always significant. So let's do a few examples together then. For instance, in this value right here, we know that the 4s are non-zeros and they must be significant. And we know that zeros between non-zeros or other significant digits must be significant. But then we learned that these zeros to the right of the last non-zero that are in the decimal place are not significant. So this number would have 1, 2, 3, 4, 5 significant digits in it. On the other hand, if we looked at the second example, we know that all these zeros that precede the first non-zero are not significant. They're placeholders for the decimal. And that makes this one non-zero significant, but also the zero that follows it to the right of the non-zero and in the decimal. There's no point in writing that zero unless it represents a place of measurement, or in this case, uncertainty. So this value has two significant figures with it. On the other hand, if we looked at this particular case, we know that all these zeros to the right of the decimal must be significant, and since the 1 is a non-zero, and this 0 is found between significant figures, in this case zeros and ones, then all 6 of these digits are considered significant. In this example, D, we know that all the zeros preceding a non-zero to the left of the first non-zero are never significant. They are placeholders for the decimal. And that means this value has a single significant digit. And in our last example, I know the 3 and the 5 must be significant, but since all these zeros precede the decimal and there's nothing beyond the decimal, these are merely placeholders, and therefore the last one has 2 significant figures. Here are some more practice examples. Why don't you go ahead and pause this YouTube video and figure out for yourself how many significant figures each value should have, and when you're done, play the video further and I'll go through them with you. Okay, let's go ahead and take a look at these now that you've tried them out for yourself. And we'll start with A. Clearly these zeros are unnecessary beyond the decimal unless they represent actual measured places, and the last case would be an uncertainty place. So these 6 plus these 2 for a grand total of 8 significant figures is the correct answer. On the second example, we have some placeholding zeros that are never significant, so the 2 zeros to the right of the last non-zero in the decimal are significant, and this value has 3. Finally, all these zeros are merely placeholders, as there is nothing beyond the decimal. Therefore, only one significant figure. And in this case, the zeros between non-zeros must be significant. The 0 to the right of the last non-zero in the decimal is significant. That means all 5 digits, including the 1 and the 8, are significant. The non-zero is always significant. The zeros between them must be significant, but these 3 zeros are placeholders. So this value has 5 significant figures. Down here, the 2 3's as well as the 2 zeros between the 3's are significant, but once again we have placeholders, so we have only 4. And in the last example, the 2 9's are clearly significant, and the 2 zeros beyond the decimal are there to represent the precision of the measurement, and therefore they are also significant, so we have 4 in the final example. The next video, part 2 of significant figures, will show us how to do calculations using scientific measurements in significant figures.